All right, everyone, thank you for coming. My name is Justin Bozonier. I work at Grubhub as a senior data analyst in finance. Actually, I think when I submitted this talk, it was product optimization specialist, but that meant nothing. So we've changed my title to something that people actually know what I do now. And this is Statistics Made Simple Through Simulation. So this is meant to be just a lot of really simple, pretty straightforward simulation stuff. A few different examples, many different examples of kind of like different ways of coming at simulation, ways of looking at statistics with simulation. So, you know, people ask you like questions about sample size, and instead of saying like, I don't know, like thousands, you can start to actually come up with some sort of like a technique of, it's not perfect, it's not like it's absolutely perfectly mathematically accurate, but it gets you a good approximate solution that is actually in line with what you would see if you did all the math. And so it just saves you from having to do the math, and it gives you just a method that you can use generally across a wide range of problems versus having to figure out, you know, many different ways of coming at the same kind of answers you're looking for. So that's the main idea behind it. So I'm just kind of curious, just to kind of get a feel for the room and where everyone's at. Like, how many of you are data analysts or data scientists in whatever form? Awesome, nice. How many of you guys do simulation-y things for work right now? Okay, cool. Like what kind of things? Just throw some stuff out. Anybody? What's that?
A/B tests.
A/B tests. Okay, cool. What do you use simulation for?
Simulating pause periods.
Okay, cool. So you're doing like Bayesian statistics stuff. Oh, awesome. Nice. Anybody else?
Monte Carlo.
Monte Carlo. Okay, what do you use it for?
Simulating market activity.
Oh, nice. Okay, cool. So we'll touch on some of that stuff. If you guys also have things you want to add to this is really just stuff I've been doing, and around me and my sphere of people, most people aren't really doing this that I see a lot of times. So if you already have experience doing it and you have other things you want to bring up and other options, we're going to be going through this. Did you guys already download like the notebook as well, or did you see that? It was kind of lately added. So if you go back to my session page, there's a place where you can go into GitHub and download the notebook that I'll be using. And the main idea for that is really that I'd like us to be able to go into that and change things and make it very interactive. So there'll be points where we'll just say like, hey, let's start playing with some parameters. Let's see what you guys come up with. See what you see, and we'll try coding up some like extra examples as well. Yeah.
So you get a link on your site.
You don't? Oh, does it have to like be approved? I hope not. Let's see. Oh, I can tell you that. That's a better idea. If you go to github.com/jcbozonier, I'll put that up here so that way you guys can see it. There will be a repository for PyData 2015. So if you go there and download that. Does everyone here like use Numpy pretty often? Most people have that installed? Good, good. Numpy is a savior. I'll also just slightly be introducing PyMC. Won't go into it very deeply because I didn't want to have everyone install PyMC on their laptops because it's kind of a pain in the butt. We'd spend probably half of the session just doing that. But I'll at least just throw it out there so people can see it. And if you've never done, actually, how many people here have worked with Bayesian statistics? Not like Bayesian probability, but actual Bayesian statistics. Can you raise your hands if you've done that? Okay, a good portion. So for those of you who haven't, for me it was a little bit of a mind melt to figure it out at first because it's just a little bit different. So this kind of gets you an idea of like what you're looking at and just how you approach the tool, and that'll kind of just get you a jumping off point for everything. So let's go ahead and I'll give you guys just a couple minutes, really quick, just to download the notebook. And then once you've downloaded it, just like throw up your hand for a second so I can see who all's done it. Okay, like a quarter of you. Give you a couple more minutes. Hi, Drew.
Is it 2.7 or 2.4?
2.7. Because I don't want to irk the library gods. Does that make your world terrible? Slightly. That's fair. And while everyone else is downloading that stuff, I'm kind of curious too. So with you guys coming to this session, what are you looking to get out of this? If anyone would like to throw out just some ideas of what you want by the time you leave here. Any ideas? How about you? You're looking at me.
I mean, I've used PyData for some past.
Yeah.
But like, just how other people were using it, I guess.
Okay. That's kind of like my same reason for doing this, is I'm just kind of curious what other people are doing, and it's nice to have some like-minded people. How about you as well?
I'm just getting more curious into the Monte Carlo aspects.
Okay. Cool, cool.
Background.
And it's in PE or PDEs? Oh, I see. Oh, yeah, that's much more precise than this. Yeah.
I'm kind of new to this. I'm just interested in adding like a little bit of questions, statistical rigor to kind of like back of the envelope data analysis.
Oh, yeah. So like a lot of times when you're doing stuff, it's more kind of just like you kind of use your data gut that you've been developing.
Exactly.
Yeah, that makes sense. Yeah. That's kind of what I started off as well. And then people kept on asking me questions, and I was like, I really want a better answer than just, and it's still like, but at least it actually is backed up by some sort of quantitative method. So yeah, that'd be fun. We'll get there for you. Anybody else have something they want to throw out? Yeah. Like a literal island?
Very small island. See how other people do things.
Oh, I see.
I mean, you can learn a lot, but how other people work.
Yeah. Where do you work?
A company called Craftsy in Denver.
Uh-huh.
There's only a couple of us doing this kind of analysis at all. We're a research shop, Python and R.
Gotcha. How big is the company? Oh, well, there's only a couple of you, so yeah, I can see that being rough. All right, cool. All right, how many people have this stuff now? We're about 80% yet? Almost there. The people who don't have it, are you going to have it? Do you want to have it? You can just watch. It's fine. It's probably more fun if you play, though. But that's fine. Yep. Let me go back over here, and we'll make sure it's at a good size. Is that a good size? Yeah, no problem. All right, where are we at time-wise? Okay. All right, cool. So the beginning portion of this doesn't really require code, unfortunately. So we'll just kind of start going through that, and the rest of you who are still downloading this thing, take your time, get it done. We'll probably spend, 10 to 15 minutes just kind of on like some of the background, and we'll go from there. So Monte Carlo simulation, mathematical models are really interesting. The whole modeling and simulation approach is awesome because you basically are just like, if you don't know how to make a math equation out of something, which is very abstract, you can basically come to this other technique and just say, well, I'm going to make code, and I have little objects in my code that interact with each other the way I'd want them to in the real world, and I'll just perturb it with a bunch of randomness and just see kind of what falls out of it. That's the basic overall gist of it. So when you're approaching these problems and you're given something some question you want to answer, there's actually like a 5-step process that I've been learning about lately for just kind of put your thought process into a formal methodology, and just so that way you make sure that you cover all your bases. That's really the only purpose of it. So in this case, the 5-step modeling approach that I've been learning about lately has been, first you ask the question, which is just really obvious, but having a concrete question that's not abstract is really, really important. Myself, I don't know if you guys have done this, have just gone off for like a day sometimes churning on some analysis, and then I realized I don't really know the question I'm asking, and I should have just thought about it for a few minutes up front. So just do that here as well, because you can go off and program something, and then you get in the middle of it, and you're kind of confused, and it doesn't really get you what you want, because you never really wanted anything specific. Next step is select the modeling approach. This whole tutorial is about simulation. So there's 2 different kind of tacks on simulation that I think I take throughout this. One is actual Monte Carlo simulation. A Monte Carlo simulation, as I understand it and as I think about it, is very, very, for lack of a better word, like simply dumb, like in a very good way, right? So if you, for example, like want to simulate people coming to your website and placing orders, like you might actually literally just generate like millions of customer objects, and you might have them interact with some website thing and click like your imaginary buttons inside your code and go through all these processes. It's very much like almost like a one-to-one process with what you would see in the real world. Then you have the idea of an analytic simulation. And analytic simulations are nice because what you can do is those areas where you have a really good idea of what's going on, you can put some sort of a mathematical formulation around those or formalism around those and say, well, this thing can be represented by this Poisson process. And I'll just pull stuff out of there to be able to sample from this really fast. But I know that basically works that way. And the rest of it you can kind of blend the two of them and kind of work with it however makes sense inside your own head for your mental model. And we'll go through some more of that as well as we go through these steps. So we select the modeling approach. We then formulate the model, which is for us going to be programming. Solve the model, which is going to be running the program. And then 5, answer the question. So once you run the model, it's really cute. You can just go up to your business owners and be like, here's my IPython notebook. I ran this model, and it saved me this answer. And they won't really know what to do with that. They're going to say, like, that's great. You have a bunch of numbers, and they're in like a list of some sort, like we would call that an array. But then they need you to take that and actually interpret it. So they have like a range. You're like, well, that's a 95% chance that the true value of this thing is going to be within this interval. And they'll be like, oh, okay. And then if you want to make it even more accessible, it's probably this answer, right? Something like that. So that requires that interpretation step is really important. And sometimes that can get missed. When we get really excited, we'll be down in the weeds, all the way down to programming something, and then going through all the steps, making sure everything works, running the program, and then you have to come all the way back up again and then look at it from someone's eyes who didn't write the program. So it's a lot of roles that we're kind of responsible for. Any questions about the modeling approach? Do you guys tend to use this like this, or does this just kind of happen naturally for everybody here? I'm a pretty disorganized person, so for me, I'm like, anytime I see a list of things I can just check off, I'm like, oh, like I don't have to think as hard anymore. I'm not going to make as many mistakes. For me, this has been really helpful. So let's see. So getting into more of Monte Carlo simulation, like what it is. And I'm sorry, the first part of this, lots of talking. We'll get to interacting with stuff. But just kind of want to set the bedrock for what to expect exactly. So Monte Carlo simulation, so there's pros and cons to it. It's not a golden hammer. You will probably, I have used it as a golden hammer in certain situations because, which is a tool that could be used for all solutions or a tool that could be used to answer all questions when it really can't. But it's really, really flexible and it's a nice tool to have in your tool belt. The main pro is that it's just this general method that you can use to give approximate solutions to any probability modeling problem. And that's from a mathematical modeling book by Mearshart, I think is how you pronounce his name. And so that's a really powerful thing to be able to say. Like you don't have to take a problem, formulate it mathematically, solve the mathematical problem, do PDE, or do like some sort of weird integral, look up on Wolfram Alpha, like how do I do this integral? I forgot. Like what is that magical recipe I need for this? Instead, you can just basically program this thing, run it, and as one of the cons says on here, your simulations are going to basically solve these things by brute force. So you might run, like I've ran simulations with like 250,000 iterations. So I'm like, it takes like 2 minutes, a minute, which is slower, but back in the day when like people were writing out a lot of the cons about this stuff, it was like 1990 or 1985, and you're like, well, 200,000 simulations is going to take a long time on some Pentium 4 processor, that's running at 200 megahertz or whatever it was running back then. But nowadays it's really fast, so it's pretty doable. You still will run into problems that you can't do as quickly, but if you're like me and you found this golden hammer, you'll just wait the half hour to get your answers done and move on. Maybe use it as an idea of like, well, maybe if this keeps happening, I'll need to learn like the mathematical solution for this, but in the meantime, screw it. Everyone at work knows what I'm talking about when I can show them this model and everything's fine. So another concept on here is that when you're doing models this way, so when you do math, it's very easy, at least from my experience, you guys can raise your hands if you've had the same experience too, where you're talking about something mathy, and you both go up to the board and you say, math works this way. And so you say, like, I can prove that I'm right. And the other person says, like, oh, all your assumptions about your stats models and stuff are wrong. This is actually the correct way of doing this stuff. And there's just this impasse. Because at some point, it's just about, well, this is what my theory says that's in my head. And the other person's like, this is what my theory says that's in my head. Have you guys kind of experienced this kind of conundrum? Yeah, I see one head nodding, at least a couple heads nodding. So what's nice about this is you can just program up a model and say, so this is how it's working. You can basically get really concrete really fast. It's no longer this soft, squishy world of abstraction and theory. It's, well, when I run it through this way and I add this noise that you're talking about, my results on the other end come out with this much variance. That seems pretty doable. You can even add in some money on that too and say, so then we're also going to assume that we're getting paid between this much and this much. And we add all that together, it means that we might lose this much money. Like, that seems doable. Do you have any issue with the code? And then they can be like, I don't like this code. I don't think it makes sense. They could do a pull request on your GitHub at work or whatever you guys end up using. They can modify your model. And then you're talking via code. You're talking via concrete problems and concrete code. It just makes everything much more concrete and much more easy to discuss. And if that person still just doesn't work at that level, it's really easy to talk to other people in the organization, like your bosses and their bosses, and just be like, look, I have this code. They could work with it. They're not. I don't know what else to do. Right? If they're not offering me a solution, then I can't really solve it for them because it seems like we're addressing every point that they care about, really. So those are the positives for me. Cons, again, brute force. Takes a long time sometimes. A lot of the stuff that we'll do is perfect through this, runs in like a second, and its production quality will be fine. And so you won't really run into that very often. But when you start doing really complex things, I did one simulation of delivery, and I put in a bunch of different variables in delivery about how long drivers could take and order amounts and other issues. And that one took a long time to run, but it just depends on how complicated your model gets. And when it does get too complicated, there's actually specialized tools for it. We're not going to get into any of those, but there's more beyond just this very simple, straightforward approach. And then the other issue is that the simulation itself actually introduces extra variation into your solution. So since you're just basically taking this model that you have and perturbing it with a bunch of randomness, it's going to cause a lot of squiggly lines everywhere. You're never going to get these perfectly smooth curves that you would get with a pure mathematical solution. And that might make some people feel uncomfortable. We deal in stats and probability. We live in a fuzzy world. I don't really care about that too much, unless that variance is so much that it's literally like I'm trying to figure out how to get a 0.5 percentage point extra on something, or 0.5% relative increase on metrics. But most of the time, the problems that we're looking at are much larger than that. People don't really care about that minute of a change. In my world, they care more about talking a couple percent, 5% increase on things, and usually you can still see those kinds of things get affected when you're doing these models. And actually, it's interesting too. So in that same book, Mathematical Modeling, the author actually says that as a practical matter, there are many sources of error and variation in a modeling problem, and the additional variation produced by a Monte Carlo simulation is not typically the most serious of these, which is actually something that made me laugh out loud. I thought that was awesome, because you're basically making all of these assumptions about your world, and if the one thing that you're most concerned about is just some random noise, then that's a great problem to have. Most of the time, the other assumptions that you're making are just, you know that they're not perfect, and sometimes they're pretty far from perfect, but they're the best you have. And so those are really the things that we should really focus on optimizing, not this little bit of noise that we're going to be adding in by doing things in an approximate kind of manner. So anyway, and yeah, so then we talk a little bit about analytical simulation. Just want to make sure I had a note on here to kind of address that. We already talked about that a little bit. So yeah, any other questions about this stuff? Do you guys have other pros and cons that you would add that I haven't mentioned here? Especially some of you guys who've already been doing this. You're like, well, it sucks when you do blah, blah, blah. I see you smiling. Do you have other thoughts? Or you? Yes, with the raised eyebrow. There you go. That's a good way to find out if I'm looking at you.
I have a comment. I've been in situations where if you tell someone you're doing it via simulation, they'll give you the condescending look like, well, you're a real data scientist. You can solve the equation.
Yeah.
I guess having a thick skin is sometimes necessary.
Yeah, that's interesting. Who's telling you that? Is that like your boss, or is it just other analysts?
It's just not a situation people have been in.
No. That's fair. But yeah, I was just kind of wondering for your context too. Is it if it's just like peers, it's one thing.
Yeah, it's the peer, like, oh, you give a talk. I'm like, oh,
Yeah.
you simulated that. You didn't solve it.
Yeah, it's like if you're a software programmer, everyone's always worried about optimizing things as much as possible. And like, oh, that doesn't run. You could run that in O of 1 instead of, or like O of like 150 instead of O of 500 or something. If you're really worried about constant time increases, or like O of n squared versus O of like n log n. And a lot of the times, like people never take a step back and actually look at like what is the value this is going to provide. And if I'm only operating on a list of 10 things, I don't really care about what the runtime execution is. It can go as crazy as it wants to. It doesn't matter. And the same thing for this stuff, exactly like what you're saying. So that's kind of hilarious. I've had a little bit of that, but it was really more just about statistical theory. And this kind of helped me get around having to have more of those discussions. But yeah, that's funny.
I think a huge pro to me is to explain it to VPs.
Yeah, makes sense. Have you been in that situation before?
Oh, yeah.
Yeah. And have you had to use one of these to kind of talk to them through something?
Yep.
How did that go? Can you tell me more about that?
I could tell they didn't understand the math part of it,
Yeah.
but when I pointed to the parts of the distribution that mattered to what they were interested in,
Yeah.
they were like, oh, okay.
So seeing that visualization of the actual histogram of the distribution of the outcome basically was a big deal for them. That makes sense.
And they made a decision based on it, so I think that's a huge success.
Yeah, that's a win. Did it not destroy your business? Because that's a bigger win probably.
Well, part of the advantage was that I got them to move to a range for KPI instead of a single value.
Oh, that's been a huge thing for me too. That's awesome. Good for you. Yeah, that was a big battle of talking about like, why don't just give us a number and then give us like standard deviations on the side or something. Like, 'cause no one knows what a standard deviation is. And like, if I tell you it's plus or minus 5%, you're saying, okay, but that's the answer in the middle. And it's like, no, it's not. So I've done a lot of the same thing where I really like these methods. I kind of blend in some of the Bayesian statistics and simulation stuff because when you're just updating data by literally just getting updated data and just rerunning a simulation, it's not pure Bayesian statistics. There's another name for it. Actually, I forget what it is, like discrete Bayesian statistics or something along those lines. But the fact that you come out of it at the end with this interval and that the answer contains the variance. So you tell someone, and they just naturally see it, like they'd see a graph, and you'd say, well, the graph is telling me that the lift in this conversion rate test was between negative 12% and positive 31%. They're like, that's kind of a huge range and doesn't tell me enough. I'm like, yes, exactly. But if I just gave them a number like, oh, it looks, the middle of its point is plus 2%. Now they think they have a positive solution. So it's awesome being able to show them that range, and people just intuitively get it. And then they're like, but now what if I want more data? I'm like, well, it's a Bayesian. You just run more data through it, and it'll narrow the more data you give it. And they're like, oh, okay. But, and they always wonder, why aren't we just doing the simple stuff, the stuff that they learned in Statistics 101? Because that's one of the things I've seen a lot is every business person has taken Statistics 101. They know about t-tests. They know about standard deviation. Everything's a normal distribution to them. And they just want to assume it and just get an answer out. But I feel like if you really wanted to just get an answer out, you wouldn't hire a data scientist. You would just get your answer out yourself. So I don't go that way. So that's awesome to hear someone else say that. So now, how many people have the notebook? I've been trying to kill time for you. Excellent. That's what I want to see. All right, cool. So we're on the part where it says enough theory. This is where Justin shuts up. And we want to talk a little bit about like getting to our first problem and actually trying to solve this with a simulation approach. Oh yeah, and just one more thing. I haven't really talked about my background at all. I actually started off as a software engineer. I did that for a few years professionally. Just kind of learned that on the go. I don't have a degree or anything to give me credit except for where I've worked, just working through like actuarial firm like Milliman. I've worked at LexisNexis before as a software engineer. I worked at Cheeseburger, if you like fun things and memes and pictures of cats, as a software engineer there and a lead software engineer, and also as a senior analyst and developer while I was there. And then now at Grubhub, I work as a senior data analyst, which we talked about. And so I've kind of made the switch over from data science. I was the programmer who knew more statistics than any of the programmers, knew more about programming than any statistician. And I've continued just kind of down that path for a little bit. So especially finding that intersection of programming and automating our jobs away, I think is really awesome because there's always more questions to answer. And if we can automate those answers, then it makes us so powerful. So anyway, sorry, I just wanted to throw that out there so everyone kind of has an idea where I'm coming from. So first problem here. So I just came up with like a really simple solution that kind of just explores Monte Carlo simulations. Have you guys ever seen like a Monte Carlo simulation that does numerical integration? You've seen that like toy example? Okay, so this kind of does that, but in a simpler way, because if you start talking integration, there's a lot of other little edge cases you start getting into. We'll do a little bit of that down below, but I wanted to start off with something very simple. So if I just basically gave you, let's see what I say on here. Okay, so you can read through this, but basically you're in a room, you're facing a large wall, because I said so, and there's a large open window in the middle of that wall, and there's a bowl full of marbles. So I wanted to find out how much of a percentage of that wall does this window take up? And so from a random perspective, like how would we be able to figure that out with a bowl of marbles and a wall with a window in the middle of it? I'm going to make somebody answer. It'll go faster if somebody answers. Throw the damn marbles, yes. So basically, like if you could just, in the real world, again, this is where it's different. If you threw them at a wall, gravity would move them, you'd have skew, blah, blah, blah. But we're going to assume that you can just make sure you'll randomly distribute the marbles across the whole wall. And then what do you do from there? Mr. Answer. What's that?
See how many bounce back and how many don't back.
Yeah. And then just divide the number that don't bounce back by the number by the total number of marbles, right, basically? So down below here, we basically do that. So I focus on first the question, following our modeling process, what percentage of that wall is the window taking up? And then this is my process for it. So count how many marbles are in the bowl, first of all. And then just close your eyes and throw marbles at the wall in a purely random way. And then 3, find the percentage of marbles that went through the window. And so down here's the code for this in Python. So you can see I kind of made like a little window. I have a wall width, wall height, window lower left, window upper right, which kind of makes a little cut out of that. I set the number of marbles. And then we can basically run that. And let's make sure this thing still runs. Go. Boop. And then go back down here. And if we rerun that code, we should come back up with a window. And then we should be able to see too. I don't want to get too fancy. I'm afraid I might screw something up, but let's try it. Let's make the window a little bit smaller and see what happens. Ideally, the window will be smaller if this is running. So that should only be 5.5. See how that plays out here. My window looks the same size. Let's see here. Let's make sure this is running at all. Bless you. Oh, this just doesn't seem to be running, period. That's going to be a problem. I'll have to fix that.
It's running on mine.
Well, that doesn't help me out at all. But I'm glad. It's good. I'm glad it's working for you guys at least. So you guys can screw with that. But I need to be able to play with some of this stuff. All right, let's see. Oh, did I close down my terminal window? No, it's still there. Oh, maybe it broke. We'll start it back up again. Okay. Make sure we're still running on the same port. Looks like we are. Pardon me, one moment. PyData workshop. This thing. Okay. There we go. So at least now something's happening. So let's rerun all of our requirements at the top. And let's try that one more time. Okay, I think it's actually updating now. So let's see. So the window lower left, so let's make this actually, say like 10. Let's see what that looks like. Yeah, there we go. Okay. So I just made like a really weird, dumb change really fast. I didn't think about it. I was like, I don't know what that's going to look like. So then you can kind of see we threw all these marbles at the wall, and these are the imprints they left in the wall. And you can see a nice little happy window where all the other marbles went through the window. And so at this point, it just becomes like a really simple geometric problem, right? We're just looking at this as I have two different rectangles, one inside the other. The big encompassing rectangle is my full area, so it's really easy to figure out the percentage. And then down here, I think I can just rerun these, and it'll tell me the amount. So with my new updated parameters, the window covers 12.2% of the wall around that. Any questions about this sample? Does that make sense to everybody? Okay, cool, great. So let's see. So then I went through a fact check session where I was just like, well, let's just make sure that all this stuff actually makes sense. So I took the wall, which I think was 10 by 5. Is that correct? Make sure. Oh, no, the wall's 20 by 10. And then, the wall height, wall width right there, so 20 by 10. And then I took the area of the window, which was the width of the window and the length and the height of the window. And since I changed that to, looks like 5 and 5. Looks like 5 and 5. Let's change this. And then we should get, hypothetically, the same answer-ish that we got above. There you go. So our simulation got us an answer of 12.2%. The actual rigorous mathematical solution got us 12.5%. We're off by 0.3%. I'm OK with that. Depends on what you're using this for, I guess. If it's life-threatening, that might be a terrible, terrible thing. But for most of my purposes, it's not usually life-threatening. It's about people getting their food delivery. And that's like an extra couple minutes, and they'll be OK. So let's see what else we have here. So moving on. Next thing. So this one gets a little bit more complicated. And it's basically taking that idea that we had there and applying it to mathematical functions and saying, and actually analyzing a statistical function. So what we're going to look at is a normal distribution. And we want to see how much area lies in this normal distribution between a plus or minus 1 standard deviation. And so that's something that everyone's heard of before. We've all seen it. But what's interesting is like when you go through statistics, you never actually just sit down and can touch these things. Like you can't play with it and really try to understand what's going on. And so with this, hopefully, and with this notebook, it would be interesting to see like other ways you might want to tweak this to actually explore just the distribution and what happens if you go this way or that way. What happens as you try to simulate out to infinity, those kinds of things. And you won't get to infinity, obviously, but if you hit like 100 or something on normal distribution, it'll be pretty close to 0. You'll get most of your answer out of it that way. So anyway, we'll go through this. So this basic idea was to take this function, this normal function that I created here, and which I ripped off the formula here from Wikipedia, just to be completely honest. And then I put it through the same kind of thing, where below my function is basically my window. Or actually above my function is my window, and my function itself is kind of like my wall. And then I want to be able to go through here. I do 5,000 samples of data, basically. And then I zip them all together and put it through a filter where I say, hey, anything that was below this line technically that counted as hit. Let's keep all those marbles, and then let's move on to the next step and see like what percentage of those marbles are actually remaining after they hit our curve, basically. And in this case, what ended up happening, so since I chose a normal distribution with a mean of 1, which you can see in here, I chose it with a mean of 0 and a standard deviation of 1. That's just your standard normal distribution, so there's nothing crazy going on. So if I chose a point that's at 1, -1, that should be 2 standard deviations, right? Or plus or minus 1 standard deviation, basically. So when I come out of this, I get an answer of 68%, and the real answer I think is 68.2%. So again, very, very close. And I did an integral, and I didn't have to know any math, except for this function, which kind of sucks. But that's easy to look up. Harder to look up how to integrate something. Although you have Wolfram Alpha, which is great. You can just integrate anything, but either way. So let's see. So then I also went ahead just as another sanity check, because it's some simulation code, stuff happens. Again, it's very concrete, so it's really easy to do a sanity check. I just graph where all my marbles went, and it looks like the middle of a normal distribution to me. So it seems pretty solid. All right. Any questions up to this point? What do you guys think? What other things do you want to learn branching off from here? Is this going in the right direction? For what you care about? Yeah, nodding heads. Okay, I'll take nodding heads. Any shaking heads? Just like F this. No? Surprising, but okay. I know you're by the door. That's totally fine. Law of 2 feet. You've got 2 feet. You can use them. So let's see what else we have here. So basic idea from a rectangular window, blah, blah, blah. So with integration is cool. So the idea is basically you can integrate like any function with this. Like it doesn't even really have to be integratable, integrable. It basically just has to be something that you can figure out a bound around, and then you throw a bunch of marbles at it and decide how you want to take the area of that rectangle and subtract out the other marbles from it. So it's kind of a cool, powerful technique. It's a really inefficient technique. There's much better techniques mathematically to be able to integrate that stuff, not just symbolically, but also just like numerically. But it's a really great introduction to the power of Monte Carlo simulation. So this is the key moral from those top 2 points, which I think is really important. So simulation is empowering us to explore statistics and probability instead of consulting some oracle. And I know normally we might get kind of put in that role of the oracle, but a lot of times the two are also doubted as the oracle. So this is a great way of kind of looking at it from a few different perspectives and coming to your answer. Let me see one other thing here. What time are we at? 10:37. Okay, cool. All right. So then the next step. So now we're starting to get into like statistical testing, and this gets a little more interesting. We'll have a little more room to play around in this stuff. Yeah. How do you verify your results are right? Well, in this case, yeah. Yeah.
Something that was more fundamental than math. Now you can actually go out of your way and start exploring complicated problems and going to things that you don't know the solution beforehand. And how do you know you're doing the right thing?
I guess and I'm not sure if this gets to your point, so correct me if I'm wrong. I'm not trying to be obtuse. I feel like that's the case with math as well. Or is that not correct? Like you could think you're doing something the right way, you could verify and come back to it, and you could still not.
With the math, you can check for consistency, and also certain things are very well established, so you can actually go back and verify that you're right. With the simulation, you can get a result. Well, of course, you have a corner case that you can check for consistency, of course.
Yeah.
I'd like to hear what you have to say about that.
Yeah.
But with the simulation, if you get to a complicated problem that you never saw the solution before, you can get a numerical result out.
Yeah.
That you don't know if it is right or not.
Oh, that's fair. And so, yeah, I think to your point, it's not, of course, going to have like a. So his question, if you guys didn't all hear it, was basically like, how do you know that these results are correct? Like, let's say it's a problem that you've never seen before. Oh yeah, what's up, man?
I would try to run it more to see if the results stabilize or not. If it still remains fluctuating, then I would run more to see.
And so your point, I think, then too, is also kind of like doing like a sensitivity analysis, where you can change the parameters and just see if the results move in the way you would expect. Is that kind of what you're getting at? Like that kind of consistency?
Yeah, or in this case, I would try more samples to see if the percentage number stabilize or it's still fluctuating.
That's an interesting point. So yeah, my answer would be along the lines of his, which is basically like, there's ways you can come at the problem where you can then say, well, like, what would happen if I changed this? And you can change it in really big, shocking ways. Like, for example, on this thing, you can make it so that way you had a really, really tiny really, really tiny standard deviation. So instead of like 1, maybe you like scale it down to like, 0.25, 0.25. You just make sure that this thing looks consistent in and of itself. On other problems, I'd look at distributions as well. Like, are the distributions smooth? Do they seem in line with the gut estimate? When they're not in line with your gut estimate, trying to figure out backtracking through it and understanding why. You can pull out, I think down below we get to a more complicated simulation, slightly more complicated, but deals with a few different distributions. And it's cool to be able to pull out those other distributions and see how is this distribution performing, and just graphing that stuff, and then being able to say like, okay, so these are all the different histograms that are feeding into this process. Like it looks like it's between these two distributions, why would this happening cause that problem to happen? And you can kind of start to isolate bits of it. But when it gets really complicated, it's really hard. And so a lot of it becomes kind of like an analysis. Like, how do you know your analysis is correct? And that really becomes a lot of, I think, more of an art. I don't have like a very concrete, great way of saying like, this is how you know this model is 100% correct. Besides also too, like, you do this, compare it to also previous data that you have. Like a lot of times you're trying to simulate processes that you currently do exist. And so you can look back at that and say, so if I take this and I apply it to this, are the results roughly kind of in line with this, and is it consistently off? And that's kind of where my head is at with that. Does that make sense? Or?
So in the past, in an academic setting, actually, what I used to do was to do the simulation and then get analytic results for a certain corner case and verify the simulation was in line with it. And also, as the guy over there said, look for asymptotic behaviors on the parameters as a variable.
Yeah.
So you know you're getting a stable.
Yeah, that makes sense. Gotcha. The edge case one is the one that makes the most sense to me, because you can basically try to constrain all the variables except for like one and just say, well, if all these other variables fell away and this one was there, I know what to expect then. So that kind of analysis makes a lot of sense to me. Yeah.
One of the points you brought up is that this is easier to convince people that you're doing the right job.
Yeah.
And then there's this possible trap there.
Yeah, no, that's fair. Yeah, no. Good point. What's that? Oh, so you want me to stand here?
Yeah.
I'll try to. No promises, but I'll keep it very, very short and in between when I walk around. I'm fidgety. All right. So awesome. Good discussion. Thank you for bringing that up. If you guys, does anyone else have a good answer to that problem? Or so how do you convince people that your simulations, you can't prove it mathematically, and you don't really have just a built-in validation or verification system? Like how you, for those of you who especially have done this before, like how do you actually show that your results are trustworthy? You said you did that with PDEs, right? Was that you? Was that you? The you. How do you prove that those are trustworthy? Do you just walk someone through math, or?
I come from an academic background where we use simulations to suggest modeling in more formal differential equation settings, and then we bounce back and forth.
So you almost use simulations to give you data to fit a model too, essentially? Is that fair?
Say you do numerical calculations or numerical simulations. Say, well, this is how we expect physics to go. Then you might do asymptotics. Solve the differential equation that gives answers. And say, well, does that match up the simulation? Yeah, it does. Oh, the simulation says I should look here. Okay, well,
Gotcha.
here.
I see. It's interesting. Yeah, in other places too, that you bring that up. Like, so there's another spot at the end where we'll talk a little bit about like modeling a short portion of a funnel on a website. And that one, I do the simulation, come up with a good variance. But then one of the ways I fact check that one, I end up just basically saying, well, if I multiply these things together, I would come up with this kind of middle answer. It doesn't give me a good idea of the variance. And then I come back and I look to make sure that that's square in the middle. So it sounds like kind of related to what you're doing. Much simpler, but one way of doing it. Anyone else? Yeah, what's up?
I wanted to talk once about agent simulation in financial markets. They create agents and then have them rate. And the presentation was fine. But then the question afterwards was, if you look at the data that these agents produce, do you see that classic volatility smile that's present in like financial times? And it wasn't there. So I think just comparing like your results versus like sort of the known
Yeah.
behavior.
Yeah. I think that's the hard part. Like if you say like there is no known behavior, it makes things much, much more difficult. Yeah.
But if you know like what it might look like,
Yeah.
and it doesn't, then
Yeah. Okay. What's up?
Similarly, if you ever had a proof you can reproduce historical data, right? As you mentioned, you'll turn this intuition, and it's kind of like red herring, and like, well, how do you know you're right?
Yeah.
So, I mean, there's often the burden of proof is on the person who's trying to actually build a reproducible model.
Yeah.
I think it's trying to use intuition, that's not the case.
That's fair. All right. Cool. Yeah, good ideas, good points. I'm glad I'm not the only person who's just looking for things that have happened elsewhere and trying to compare the models to that. So that makes a lot of sense to me. All right, so let's talk about this a little bit. So now statistical tests that make no quote unquote assumptions. They always make assumptions. We at least assume that everything is IID, independent distribution or independently sampled. Each sample doesn't affect the other sample. All this kind of basic stuff. But for the most part, you're not talking about doing a normal test on something. You're actually just going to say I want to just take this data and compare this set of data to this other set of data. So we can start with this portion. So in this split test, let's see what we have. So I've just basically generated some data from two populations. And in the simulation world, what's kind of cool is that since you're doing a sim, you get full control of everything. It's kind of like a God complex. It's amazing. It makes you feel so good when you go home at night. In this world, you can basically say, so I have my control, I have sample A, I have sample B, and I can actually just say, well, I know this one is going to be, in this case, sample B is going to have a higher mean than my other sample. So when I'm doing my tests on how I use my statistical methodology, I should be able to see this come through on my test. And so that's what we do here, basically, except I also make the tests uneven. So one of them, I get 40 samples out of it. The other one, I get 20 samples out just to try to introduce some differences in how variable my results will be. And so with Numpy, basically, I can just pull out 40 samples all at once and then 20 samples for sample B. And then the key thing in here, this is called bootstrapping. I could basically go through and sample from that distribution, and I can pull 40 things out. But it doesn't mean, and it's with replacement, right? So I pull 40 things out at random, but every time you pull something out, you put another thing, you put it back in as well. So that way you always have the full data set. And then you get the mean for that, and then you build a distribution of your means. So that's kind of a lot in one line of code for what's going on. But the basic idea is down below, where once you do that sampling, you'll see that the one that has a lot more samples is a much narrower distribution for the mean, which I think makes sense. And then the one that has fewer samples has a much wider distribution. And so we're trying to say, hey, if we compare these two things, which just visually, we're all data people, you can see one is definitely different from the other. But from a statistical perspective, you say, okay, so I have these two different distributions. How do I apply some sort of a quantitative analysis on top of this to give me to actually quantify how different these two distributions are? Does that process make sense, the sampling and then taking the means of samples and making sure the sample sizes that you're taking the means of match the sample size of the actual distributions that you got from your experiment? Yeah, okay. I see one nodding head at least. Yeah, go ahead, hand up.
So it seems very sensitive to very non-robust, because on repeated runs it is very, very different results, as I was trying to write.
Yes.
So how to know which one is objective result that
Yeah. No, that's a great question. So, and I think you're referring to just these distributions, right? Just how variable they are? So that's a great question. So this is actually what we want to see. This is basically saying that we have this distribution of things, and here I can actually print that out as well, just so we can visualize it a little bit more. Let me go down below. Oh, you liar. Okay, let's try it one more time. Boop. Recreate another one. So now it doesn't match what you guys have, but that's fine. So this is what ends up coming out into my sample A, and then sample B looks like this. Okay, so we have all this different data. And so we're basically saying, so I'm just going to pull, and we can actually even do that kind of on the fly here. Let's see what this looks like. Pardon. Let's put that right above these guys. Boop. I, a lot of times, like to make sound effects as I click on things because it makes me feel better. So there we go. So I can just keep on pulling, basically pulling back a sample of 40 things, getting the mean of it. And so why does this vary, right? This is the whole concept behind actual classic statistics that we normally would use. You have this data sample basically, and by you just randomly sampling from it, you're somewhat approximating the distribution that it's supposedly actually governing this distribution. But there's a lot of, the less samples you have, of course, there's a lot more unknowns to it, right? There's a lot more variation that can occur, and that's just the math. That's how these things behave. So that's exactly what we want to be able to see, is that we have these crazy, widely variable distributions, and this is just the first step. This is okay, so now you have these distributions, you've shown us the variation in the mean. If you would have just resampled this thing a whole bunch of different times, and we're using bootstrapping to try to approximate us sampling from the quote-unquote actual or pure probability distribution this stuff would come from. But then basically from here, on our next step, we actually will see how to compare these two distributions. Does that make sense? Is that kind of like what you're looking for, basically, is how do you start to compare these things? So let's go down a little bit. So what's cool about this, first of all, I guess I'll say this, is that by just having these distributions, you can already give someone a range of, or I guess you would call it, in this case, we would talk about a credibility range, or credibility interval. So for example, on the blue one, you might be able to say it's 95% probable that the true value would be somewhere between what, like, say like 13 to 18 or something, just guessing. You can actually get this mathematically. We'll do it down below, but for right now, we'll eyeball it. So say like 13 to 18, and this other one might be somewhere between, say like 16 or 17 to 26. So that gives you an idea that you already have this estimation of just the individual experiments and how they went. And now it's like, okay, so they're both different, they overlap, but do they actually vary those still? Because just because they overlap, maybe they could still vary by enough margin that this would be a significant change depending upon the percent. Like your, not p-value in this world, but close to your p-value, your probability that you actually have a true difference. So as we scroll down here, I do another analysis where we take both those samples together, and I just take the difference between each one of the paired up samples, because they're all in random order and stuff. I haven't sorted them or anything. So I just say like, okay, you're in random order. I'm just going to take the differences of each one of you guys. I'm going to group you up as pairs, take your differences, and just see what those differences end up looking like. And that's where we come up with this histogram. And I'll rerun it for the new data that we have above. And so this histogram actually gives you an idea of the actual shift of one distribution to the other. So in this case, what you're trying to do basically is say, so if I get a, you actually have a couple different ways of coming at this. You can say like, I just want to find the credibility interval in the middle. And I'll say like, in this example, let's say like it's 95% chance the true value of the change is somewhere between -10 to 0. Since it includes 0, you're like, it's right on the edge, but it includes 0. Can't really say that it hasn't changed necessarily. Like it might just be like an odd edge case. But another option that you can do as well is just say, well, I just want to know if this is less than 0. And if you want to do less than 0, you can basically just find the probability of all data that's less than 0 in your distribution, and you can come up with that way and say, well, in this case, maybe you would say like 95.5% of the data lies at a point that's less than 0. So yes, it is less than 0, and we can move forward with the analysis. It just depends on how you want to look at the histogram that you have. And down here, I do the credibility interval, and it shows it's, I was off by a bit. -14 to somewhere around 2 is actually where the true value of this thing lies, of the difference. And then you can see as well, if you go back up to the top, we could just pump up the sample size to your point and get rid of some of the variation. Rerun that. Let's do more. Let's try this with 250 and 250, and let's see what that looks like variation-wise. So you can see as I'm adding more samples to it, these two things are getting narrower, reducing the variation in the data. And that's still, we can try that. Let's see where that leaves us at. So we'll go down. Let me delete this stuff since we don't care about it anymore. Boop, boop. And then we'll rerun this. And then we'll rerun this just to get our actual answer. It's still not quite telling us too much. We'll throw more samples into it, see what else goes on. Let's go. Oh, did I screw something up? Let me see. Oh, you're right. Oh, that's terrible. Let's fix that. Thank you, guys. This is why you shouldn't duplicate code. Right here. Just trying to teach. That's all. There we go. That should be pretty obvious. So let's go back down. Let's see what we can do with 40 and 40, since I was just ridiculous. Boop, boop, boop. Oh, even at 40 and 40, it's much more apparent. Rerun it, probably get some different samples. No, really. Okay, so let's go back down here. All right. So by bumping up the sample size, now we have an answer that's somewhere between -5 and -9. I'll run this thing to give us the actual answer, -4.5 to -9. And so you're like, yeah, this is definitely negative. And you can see as well, what's nice about this is if you're talking to your VP or you're talking to other people, you can kind of explore the model like I was just doing, like, oh no, see, this works. And like I do this, and how come everything's staying the same? And basically just keep on kind of try it from a few different edge cases and see how is this actually changing the world. And sometimes you can just do it for fun. I have another one down below where we kind of examine, well, I'll show you. But anyway, yeah, you can kind of just explore statistics themselves and just kind of see how does this affect the way this will statistically come out, basically. Yeah?
Could you scroll up
Yes, sir.
Could you explain the sample A sample? So it's taking a random sample,
Mhm.
sample A, taking like 250 samples of it and taking
Yeah.
and then it does it 10,000 times.
Yep.
So I changed 10,000 to 1,000 and the whole magnitude of these curves changed by a lot.
Yeah.
I thought I should not.
No, that's awesome. So that's great, and I love seeing that you're playing with this stuff. So that's the whole point of me giving you guys notebooks, is you can just kind of be like, oh, that's weird. What happens if I change this? So this is interesting. So this sample size here, this 10,000 versus this other one. And I know you're not necessarily confusing them or anything, but just to kind of, since you're hitting on that point, just to dig into it deeper. So this sample size actually affects our answer. Like they both affect our answer, but this one actually affects really like the whole statistical side of what we're doing. The other sample size, the 10,000, that's literally just almost like a resolution. So the more we turn that up, the finer grained our results will get, and the smoother our curves will be. We'll see data at a more precision, at higher precision, basically. I think is the way I would tune that. So in this case, 10,000. Let's see what happens if we move it down to 1,000, like you did. I'm guessing you should get something at least extremely very coarse. It'll look like this. Looks pretty normal, like pretty good normal distributions. We do this, and it starts looking really terrible. Yeah. That's just because we have less count. Oh, that's why. Oh, okay, cool. Yeah. So that's one of the reasons. I'm not normalizing these, and so we're not actually seeing percentages here. We're just seeing magnitude of the number of samples that we have in each of these different groups. But the other point, too, about now they just look a lot spikier, you'll see. And that's something that we'll try to start to look at fixing when we go down below for, this is bootstrapping, and we'll start talking about Bayesian bootstrapping a little bit using a Dirichlet distribution. But yeah, so this one doesn't have to use any kind of special distributions. We're just using like the data that we received, and we get this. And then as you keep on, if you went down to like 100, for example, this would look terrible. That's just, ugh. And then we go through, and if we were to do the rest of our analysis, let's see what that looks like. Wow. This is how you check your results. This is another way. And we get -4, negative. It's just, it's terrible. And then if we pump this thing back up to 10,000, and again, this is why for simulation, it's like, oh, we have to do 20,000 iterations. Wow. But it's like 2 seconds. It's not a big deal. Let me go back through and update this really quick. And then I saw like 3 hands all at the same time. Let's go with you first. Yes.
Just a question for the understanding. So what you call sample A and sample B, that would correspond to the actual data that you have.
Exactly, yeah. So sample A should actually really be like control. Sample B should be variant data, basically, yeah.
Exactly. And then out of this actual data, you take a subset, which you in the following way. How do you decide, when you do this example, you choose exactly as many data points as you have in the sample, but randomly.
Yeah.
Why do you choose exactly as many? Is there any
Yeah. There is. The reason why, because what happens, let's actually explore it too. So let's say like, because if you change, so like for example, down here, we're sampling out, we actually saw me run into this problem. When I wasn't changing these, the distributions were staying the same, right? So this is all about the number of sample sizes that you have, especially when you're talking about the mean, is what reduces variance from the means that you're sampling from this distribution. So if you made that to some, like a lot of people I know who've done bootstrapping, they'll be like, and then you just sample 500 things out of each distribution and you come up with some distribution. But the problem with that though is that you didn't actually measure 500 recordings of data. And so it looks like you have less variance than you actually do. So if I were to pump this up and I said, hey, well I only have 40 samples and so everything should look like this, but now if I turn this to say that I have 1,000 samples, or let's say 500 since that was my example, just to keep everything consistent. Now we'll have much less variance, but I haven't actually gotten new data. Actually should have less variance. Let me see. Yeah, more samples I should have less variance, but did that actually happen? Oh no, that's why, because I wasn't using this 40 and this 40. This whole thing. Let's do this. Sample size. Again, don't duplicate code. That's what this is all about. There we go. So now if we do this, we'll have one example like that, which is very wide because we only have 40 samples. But now if I were to say like, oh no, I want to do this at a different amount. Let's say I do 500 here and 500 here. Now I should have much narrower distributions. But that doesn't make any sense. There's no reason why I should have less uncertainty now just because I did my test differently. You know what I mean? Does that make sense? Okay. So that's a really big thing. And that's actually what also becomes an issue as you continue doing, like I've done simulations before to do like a power analysis for tests that needed like 200,000 samples. And I'm like, oh, I hope that this technique works up into that. I've never tried to pull 200,000 samples out of Numpy before, but it did. It just took a really, really, really long time to do all the math I needed, or to do all the simulation that I needed to do. But you basically have to say like, oh, okay, well then I'm going to sample 200,000 things out of this top one, 200,000 things out of, and they take means of the 200,000 things like 10,000 times, so I can get my curves, and that's where all these numbers kind of start piling up on each other. Yes, you're the persistent one who still has their hand up. Thank you. What's up?
What would you say is like the easiest way to screw up doing this?
What I just did, which is just mixing up your variables and your values, is a really easy way to screw this stuff up. Variable naming is really huge. So like when I do this for work, like I'll just go through and be like, and I spell out everything. I don't really like to abbreviate a lot of stuff. I'll be like control, or I'll be like control pop, or control observed data, or something like that, variant observed data. And it's a really tedious process, but I'm really nervous about being wrong. And so I'll just type everything out and go through it, and then try changing some of these numbers. I mean, really, it's like any analysis. Like there's no one there who's really going to help you not screw it up. You're just going to get yourself in trouble. So it's the same kind of techniques you use in analysis, where you're saying like, is this data consistent with what I would expect? If I change this value, does this happen? Blah, 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 blah. All the stuff we talked about for the other question as well. There are a couple other hands up. Yes?
One question that was interesting, you kind of brought up like, narrower than should be given the actual sample size
Yeah.
compared to the, greedy upsampled size. So like, I was just interested in some, generative data approaches. I was wondering if you had any experience with like rule of thumbs to like, okay, this is how much actual data I have. This is how much I can sort of play it out, right, in the future with fictitious data.
Oh, so are you saying, like, just how would you generate data for this stuff?
Well, assume that I can generate the data, but it's the artificial narrowing, right, which you're trying to avoid, like.
Yeah.
Yeah, so you can narrow it somewhat and have some cool, like, futuristic scenarios, but like, you see what I'm saying, or not really?
Not really yet, but keep trying.
How much substantive data must one have? So like, what's a good ratio, for instance? Like, if I have 40 samples of real data, how much generative data?
Okay, that's a good question. So in this case, for statistical analysis, you don't have any generative data. Like, so I'm not, or I should say, it's all based on the actual data. So where I'm doing this np.random.gamma, that would be replaced with actual data. So both these gammas would be replaced with that, and then down the generative process is the means, where we're sampling from that observed data. So that's really my answer, I guess, is that you start off, everything comes from that data, and then from there, there's not really like a rule of thumb. Like the more data you can generate, the more precise your results will be, which is kind of nice. Does that answer your question? Or am I off now?
No, that's cool. We can get more into that later.
Okay. Am I really off? Am I not getting it?
What? No, that's the right answer.
That's the right one. Okay. Just want to make sure I was somewhat in line with where you're going. Yeah, what's up?
So adding on to that, how do you know where to stop? Because with these parameters, with actually 250 and 40s, I can see variations that go really wide apart to completely overlapping.
Yeah. So that's an interesting question. So especially like you're talking about like in real life, like if you're running a test. Yeah. This is the thing that that seems to catch a lot of people, and it makes sense. So a lot of people, when you start off doing a test, they're like, but I just want to know if these two distributions are the same. And you will never, ever, ever, ever know that. Because you're basically asking, down here in this distribution that we come up with, you want to know that this is all centered on 0, basically. That 0 is like the bin. But when you're doing, and so I'll get to it. This is kind of a long answer there, just kind of giving some theory on it. So like we have this probability distribution, or this frequency distribution, however you want to call it, for the answer. And so we basically find the answers by summing. It's basically like an integral, right? We're summing up the area underneath this curve, except we're doing it in a discrete way. So we just add up a bunch of bins, and we have a probability that way. In the case where you're trying to say like nothing has changed, you're basically trying to say that you want to take an integral from like a to a on this function, and it's never going to be anything real. I think Gellman talks a lot about, Andrew Gellman, he's like a big Bayesian statistics person. He talks a lot about that any statistical test that you run, like if you're ever running like an A/B test, and someone asks you like, well, was this a no change? You can always just tell them, no, it's not a no change. You changed something specifically, unless it's an AA test, you specifically changed something in the world, it's going to have an effect. And even in an AA test, you're not capturing the exact same people, so there's always a change. And so that's always really important. So in the case of like wanting to know how far to go, the reason why that all comes back around to this is because it could just be too that these are just the same distribution. So let's say, for example, that we put the same distribution in here. So let's actually make this a 3.5, And let's say, let's fix this before this bites me in the butt for the third time during this presentation. All right, so let's say we do that, and we run this at, or actually, you know what? Let's even stick with the thing where there is actually a change, but it's super, super small. And I just want to know exactly how much I changed it by. So let's say by 1.025, 2.5% change. We run this. Yeah, it's really hard to say that that's a change, right? And then you go down here, and so someone will be like, well, I mean, especially this, that's a pretty symmetrical distribution around 0. It really looks like there's no change. So how do you know to stop, or how do you know if like the above actually was shifted? And the only way is to keep running more data through it, and keep running more data through it, and keep running more data through it, until finally you just say, look, like this whole thing's about probability. We're never going to know for sure, so there's always some sort of a risk. So a lot of times what I'll talk to people about will be like, or the discussions I've had, for example, when I wasn't in finance, talking to finance about split tests has been like, we'll look at it from the perspective of, we have like 2.5%. How many samples do we have to get in order to get that level of risk, basically? And then you're like, well, 200,000 people, it's a lot. Like, do we really need to do that many? And then you'll just have more of a risk-adjusted discussion about it, and it'll be kind of a back and forth negotiation. And when you get to that limit, like wherever you decide was your limit, stop. And if people want to keep on testing it, they can, but that really can just slow you down, because then you just churn. You're just like, well, especially because people have these ideas in their head that, right, the development teams or whoever you're working with have created these tests, so they really believe in them, or else they wouldn't have put their time into them. It took them like a couple days, maybe a week of time to make this test, and they really have a strong bias that it's going to improve the world, and it's going to improve the product. And so it's hard for them to see this running and just never get there and just be like, well, it hasn't hit significance yet. I think the key thing for me when people say that is significance isn't assumed. We start off with assuming that it is that significance. There's no evidence of change. And from there, you have to prove that there's a change. And I think that inversion of the mindset is really, really, really important, because that's all it ever is. Like when you look at, I think that's actually a really big foundation of classic statistics, is that it teaches you from that point of view of just, you can assume everything's the same until you see evidence of something different. And then from there, now you have something. But to just say, how long do I have to, basically saying run this until significance means to me, I want to run this until you can show me that there was a change in the two groups. And that's just not the case with most tests that anyone's going to do.
When you
Yeah.
think you have significance is also a mistake. Like
Oh, yeah.
Like people screw that up all the time.
That's a good point. And in the Bayesian world, I think it's a little bit less clear. Yeah, frequentist more problem. But also it's interesting too, because like so often Bayesian statistics and frequentists agree pretty damn much the same. And so I've always wanted to run that simulation, is like, what if you treated frequentists like Bayesian and you ran Bayesian side by side with the exact same data? What kind of stuff would you get? I haven't run that simulation yet though. But yeah, to your point, like one of the big no-nos is just stopping when you hit significance. But in the Bayesian world, you end up with, you're looking at actual probabilities, or at least you're thinking of them in terms of probabilities. And so you're saying, well, once I see enough data that I can say it's a 95% confidence, then, or 95% probability that my value lies in this range, or that I have a lift, you're pretty good, and you just kind of stop. But yeah. Other questions? This has been a really, really good one so far. Anyone else? I think I missed some. Yeah.
Given that you have two distributions that are overlaying each other, have you ever tried determining membership distributions? Determining, like, let's say that you have these two here, you want to determine, but you only have a view of, let's say, one color, let's say gray, and you want to determine which one is in the blue and which one's in the green. Have you ever tried to separate them?
Which one is the blue? Excuse me, this probably sounds really, really ignorant. But so then what you're saying is like, if you just collected all your data into one pool, and then after the fact try to separate them out?
Let's say you have a distribution that looks like this.
Yeah.
Kind of like two.
Oh, like bimodal.
Trying to say, I want to determine which time for membership, basically.
I see. So you're saying like, what if our control group was bimodal, it had two different humps, and then trying to separate out those two different distributions from each other?
Yeah, I can give you an example. Let's say that you have geographic imagery, and you're looking at the growth of corn versus the growth of wheat, and you want to determine which one is which, and how to separate those two distributions.
Gotcha.
It's kind of a hard problem, and I wonder if you've ever tried to do this.
No, I mean so A, TLDR, no. Second point, thinking through it, I think it's interesting because it almost sounds like a classification problem to me. And so like, for example, like if you think about it from like the perspective of like a naive Bayes or like a Gaussian naive Bayes, right? Where you actually have kind of like all these different models, and you're basically just going to say like, like I can imagine this from like a conditional probability perspective where you say, like, given that it's this value, which one of these is it more likely to fall into? And so if you could model that first distribution and model the second distribution as this is what I would expect these two models to be, and then you could just do a probability based on that. Because you can say basically, like, given this data, this is the probability it came from this model versus this model, and just have it go in the one where it's the right probability. But I also can imagine that making some really weird shapes in your distributions and then not being correct. So no, I don't know, but that's an interesting problem. Do you actually have to deal with that?
Someone is doing the example I gave.
Mm-hmm.
They're trying to determine the price of corn versus wheat, and given a certain time of the year, there's a distribution that a lot of times overlay each other, and it's very messy. And they need to separate, pull out the observations from wheat, so that way they can determine the price.
Do they just have like the market price, like how much people are spending on market or something, basically, and they're trying to figure out the components of that price, essentially?
Determine yields, that way they can determine the price.
Huh.
And that way you have an edge.
Interesting. Yeah, no, I don't think I have enough context for that, but it sounds very interesting. Other questions? Yes. How? I'm using, what is it, 95 as an index? 2.5. Oh. Yeah, 25. Oh, so this is another issue. So let's talk about that. So we have a sample size here of that. We have 10,000. So the way I got to that was I basically just said I wanted to get 2.5% into each tail, and that should be 250 with 10,000 samples. So what I should do to make this better is say, like, let's call this my resolution number. Put that in here, put that there. And then down here, what I should do is say int of 0.025 times my resolution, and then do that on both sides. And that way I'm getting 2.5% on the left, 2.5% on the right. And if I do this intelligently like this, does this make more sense? Yeah, go. If it worked. Resolution is not defined. Oh, darn you. Let's rerun this. There we go. All right, cool. Other questions? I think there was one more. No? Two more. I'll go with you.
Quick question. Is the bootstrap sample size always equal to your original sample size?
Oh, that's the way I do it, yes.
Is it always like this?
Well, if it wasn't like that, your variance would never change. So the sample size that you're sampling out of your distribution to get your mean, if you don't change that, it's always going to your sample size is always going to stay the same, and so your variation stays the same, and so you won't actually be learning more. Does that not make sense? What are you thinking?
I think because the original sample size does not change, so it simply increased the size of your bootstrap sample size should not give you more information because you don't have.
Oh no. Oh, so you're not talking about. You don't mean this number. You mean this number, the resolution number, right?
The sample size, that's the bootstrap sample size.
The one that's right here that I'm pointing out, right? Yeah.
Is it always equal to the sample size used up there, like on the second and third line?
So I'm saying yes. And so are you thinking there are times where you wouldn't want it to be?
No,
Or are you just curious?
I'm just curious.
Yeah, it should always be the same. Because that way, when, again, like for the example of, let's say like you had more samples, but you decided to go with 40 instead. You have all these extra samples, and so they might give you like more like roundness to your curve or whatever. Like they might give you a little bit more precision in a certain way, but you're never going to get the variance actually reduced as a result of that. Like so, in order for you to see, like when we're talking in statistics and we're talking about reducing or making the signal clearer, we're usually talking about reducing variation. And in our statistical testing, the main way that we do that is by adding more data. And so if you don't represent that in your model, you're never going to see that you have a reduced variance. And so it's going to look like you haven't actually reduced any unknowns yet, or uncertainty.
Can I make the following statement? If
Yeah.
I do bootstrapping in this way, then the distribution of the mean that I computed from the bootstrap sample is going to be the same as or close to the distribution of the mean that I computed from by sampling from the actual population.
Yeah, no, the distribution should be the same thing. No, this should actually be like the same thing as sampling like a mean from the population. That is correct. Yeah, that's why we do it that way. Yeah. And again, just to make sure that this is obvious, like this is not like if you had real data, that would replace this. This is just to generate my fake data, just to make sure I'm clear about that. Yeah, you had a question. Go for it.
Similar one. So in the while ago, you had the bootstrap sample size, the second row for when you're actually doing the bootstrap samples, go higher than the original data set, and that is not a good thing.
I'm sorry, you're saying that the original notebook before I updated it, or?
Or somewhere in the middle, you updated it to be 40 and 250.
Oh yeah, and that was terrible.
Okay.
Yes, it should be the same. And that's why, like, because I wasn't using an actual variable name to capture that, so I changed it and named it out of whack. So yes, thank you for pointing that out. And he was saying basically, so back where I had 40 and there was 250 later on, was that just a mistake? And I was like, yes, that was terrible. Bugs. All right, and one other question I think I saw. Yeah.
I just wanted to ask, your explanation you gave seems different. Before you said you should make the size of your bootstrap sample the same as the size of your data, because if you made it larger, you underestimated the variance.
No, it reduces the variance, which is good.
You reduce the variance of what you get out, but now you just said your variance wouldn't change. It almost
No, because his point was like, at least the way I was interpreting what he said. No, that's fine, yeah. Just to give kind of like how it all fits together in my head. With what he was talking about, I was trying to say that if you had more data, but you kept the sample size the same, that you're sampling out of it, it wouldn't help your variance at all. You're still just sampling the same number of points out, basically. So that was the difference I was trying to point out. Yeah. Right. And I think it would actually maybe give you more precision in a bootstrap because you just have more data to pull from, but it wouldn't reduce like the variance. I wouldn't expect that. That's all. Another one? Okay. This was a dense topic. Lots of questions. Good. Glad. Thank you. It's always terrible to be up here and just talk at people. So the more we talk to each other, the more warm this whole room feels, and I appreciate that. So let's move on to the next one. So this next one is parametric, but it's not parametric in the way you think of it. Like parametric just means any kind of distribution where we have parameters to tune. And so really like any probability distribution where you have like a function you're going to plug numbers into, parametric. Even Dirichlet. How many people are familiar with the Dirichlet distribution? Oh, people. Oh, that distribution is love on a hot summer night. So, we should talk about that a little bit. Well, let me put that down here as an extra credit. 1 sec. Actually, we'll get to it when we do the Bayesian bootstrapping, so we can wait till then. We have 45 minutes. All right. Yeah, we'll talk about that. So even the Dirichlet distribution, which technically has an infinite number of possible parameters you can tune, parametric. But for our intents and purposes, it's really just parametric in that it obeys like the laws of probability. And that's pretty much a good enough type of a set of assumptions where you can get by with just about anything. But we'll talk about that. So anyway, so parametric tests. So what we're going to do here, this is more of the analytic simulation that I was talking about. So we'll actually take probability distributions and we'll sample from those rather than sampling directly from our data. And one of the key things that we get out of that is, and I can actually illustrate this. So actually we saw it a little bit. So on the bootstrap, if we went down to a very few number of samples, and again, this is what's cool about this, is that I can just show versus having to help you guys understand theory and help me understand theory. This gets really, 1 second. Sample size of 10, 10. Then we have the means. Oh, the means will still come out looking fine. So let's see, down here, what do we end up with as well? A little funky. Let's try this. What's the point where this starts breaking apart? So at some point this starts breaking apart, depending upon the distributions that you have. And it's fine. This thing should still have a crazy wide variance and stuff, but the data just starts looking really weird, really wonky, and it's so far away from like an ideal view of distributions where you just kind of get a little bit uncomfortable. You don't really have to have that much of a problem in an analytic simulation kind of world because you can basically make sure that, well, I'll kind of show you what we're talking about. So let's see here. So we have parametric tests. So in this case, what we want to do is say, if we have like a coin, just the standard coin flip example, we can do that using the standard bootstrap approach that we were just using up above, where let's say like I had this array full of like observations, 0 is heads, 1 is tails, and I want to know, is this thing a fairly weighted coin? Is it 50% heads, 50% tails? I can do the same thing we did above with bootstrapping, but to solve this problem. And this is not the typical way people normally solve this. A lot of times you'll see them using like a beta distribution and stuff, but it's actually interesting that bootstrapping generalizes, or this problem generalizes really well into bootstrapping still. So then down below I form this distribution. You can see how bootstrapping does with it. And you can see too that, let's see here, so we have that, sample choice. We have, it's not the most ideal distribution in the world, and it gives you an idea though that it's probably not a fair coin. But then what we can do is we can say, well, if it's probability, we have a pretty good idea of like the distribution we can use. We can use a beta distribution. Is everyone familiar with beta distribution? Yeah? Show of hands, maybe? Okay, cool. All right. So we can use a beta distribution basically, and instead we can just sample from that. And then we can sample like a whole ton from that and build up this very, very much approximate view of what an ideal curve should look like. And then we get an idea of where this probability is actually like mode-wise centered at. It looks like it's more around like 10% or something. And then we can keep on running data through it to try to get to a better answer. So this is the analytic simulation for it. It's much smaller. It's very simple to do. This isn't that much worse. It's one extra line of code, but let me see as well. So we have the mean there. 10 bins. Oh, I see. Okay. Yeah, so this one's nice because you can kind of just keep on resampling just to continue smoothing out the curve. And I know we probably all have done coin flip-ish type things in the past as well, so I won't waste too much time with that. What else do we have here? Sample coin flips. Oh, so this next one is the Dirichlet. So this is fun. So up above, we're using the beta distribution, and we're basically saying, so the number of times that we flipped tails, which I think was 1, and heads, which I think was 0, then let's just keep on sampling from percentages from the beta distribution basically, and let's just plot all the different percentages that we get. And the percentages that we sample out of there just end up forming this curve of what we could expect all our different hypotheses being. So for like those of us who haven't gone too far into Bayesian statistics, the idea is that in Bayesian land you enumerate basically all of your hypotheses, right? And then you basically can look at each one of them, you give them some sort of a base probability to start off with, and then we just go through and we enumerate every single hypothesis possible. And so that ties in really well to the simulation stuff because it's fairly brute force, but we get something out of it too. Like in this case, I basically had to take from this beta distribution, I basically kept on sampling probabilities out. And so it's like, okay, here's another probability. And then when I graph it, it basically sets up all my different hypotheses for what the probability could be that this coin is going to flip tails basically, or flip heads. And you can kind of just see that happening here. So you have like every possible hypothesis between 0 and 1, but not every, because every would be like a real number line and it'd be infinite, but it's discrete. But you can bin it into 1 percentage point bins, or you can go as far down as you want to 0.1 percentage point bins, whatever you want to do. But you do have to bin the data because all this stuff is discrete math. So we do it that way with the beta distribution, which is cool. But then we also have the Dirichlet distribution. This thing is awesome. So Dirichlet distribution, what it can do is it basically says, if you just have like a wad of data, like above, for example, where we had all those different data points, like currency is really good to test with a Dirichlet distribution. You can basically, if you can just bin it, and you can bin it all into like penny amounts, so you say 1 cent, 2 cent, 3 cent, all the way up to $10, 20 cents, $100, 1 cent, et cetera, for however wide you want to be able to consider. You can basically feed it into a Dirichlet distribution, and then you can sample out of that to give you an idea of what your mean should be for that distribution. And the Dirichlet distribution is really just a generalization of the beta distribution. So it's the idea that, like, let's say you have dollars, for example, and pennies is what we're using. You could basically just say, like, so if I got in an order for $20.02, then I can count that as one observation for that. And now and let's say I had between 0 and $100 on there, right? So it'd be, maybe I have an even prior on all that information. So I'd be like, so I have 2 samples for this and 1 sample for everything else in my range. So it makes it much more likely. And then you get another sample. And then you should start forming basically like this very, very, very large set of distributions basically. So we do that here, but we only use like a 2-case example. So where we say we have the 0 spot basically represents, I think I said heads, and the 2 spot represents tails. And then we can feed this into a Dirichlet distribution and get out the average of that data. And then we can also fill up this distribution that way too. So we can come at this data. It gives you the exact same curve, but just in 2 different ways. Let me try doing this. The Dirichlet thing is not sounding crisp. Let's try this out. So let's say we had, how many things is this? This is 8 things. So this is what happens when you sample from a Dirichlet distribution. So we're saying like, okay, so I have 8 different bins that my experiment results are going to fall into. And just because I am being a good Bayesian, I just choose an uninformative prior, quote unquote. We'll talk a little bit about the fact that that gets really weird in this situation. And I don't have a great solution for it. And so you do this, and then you'll sample out of the Dirichlet distribution, and it pulls out one sampling of what the possible percentages could be for each one of those bins. So all these things will add up to 100% basically. And then every time you sample from this, since you basically have very little data in here, you'll end up getting just wildly crazier different results every single time. And so you can imagine basically that you just are saying like, well then if I want to have one thing, we're saying maybe we do 1 and we do it times 100. So then we should have 100 of these things, right? Yeah. So now the Dirichlet distribution is actually handling for us like 100 different hypotheses. And when every time we sample out of it, it's like, oh, well then it's technically feasible that the first bin has some crazy small value with 5 zeros before it, et cetera, et cetera, et cetera, et cetera. And then you can basically start taking then you have to weight this average. This gets a little more complex. You have to weight the average with the values that each one of those represent. So let's say, for example, that, let's say these are dollars, just to make life easier for us. We can do I for I in range 100. And so these would be bin values. This is like bin keys, I guess I should call it. And this would be bin values. And then, hypothetically, what you can do, because it's NumPy, and NumPy is amazing, I have to make this into a NumPy array, np.array. We can basically multiply all the bin keys by the percentage for observation inside of the bins, right? So this is saying that, for example, let's take this first bin here. So it's saying that's the probability of getting $0, let's say, if these are dollar amounts in our bin keys. So that'll become 0. This is the probability of getting $1. So multiply that by 1. The expected value then would be this number, right? This one is the probability of getting $2. Multiply that by 2 to get the expected value for $2. It's 4.28 something times 10 to the negative second, et cetera, et cetera, et cetera. So if we do this multiplication, we'll see that kind of happening. I just resampled, so of course it destroyed my point. But you can kind of see that same thing happening. We have 0 here because 0 gets us no money. And then it gives us the expected value for every other bin. And what's cool about that, just to resample yet again, is that then we can sum that up. And the expected, since we just have a bunch of expected values, we can sum up and that'll give us our average, which would be $47.69. And so that's, again, like how do we know, like how do we actually gut check this stuff? Well, if I don't know anything and I have a range that's between 0 and 100, I expect it to be somewhere around $50 on average, I guess, because you're talking about a mean and that's in the middle. And it couldn't be like $0 as the average because there's nothing on the other side of 0 to help weigh the average down that way, right? So this makes sense to me that that could happen. Let's run it a couple more times, or actually even what we could do, if you want to get really fancy and understand it, you do in range, we could build a histogram out of it. Boop, boop, boop. Again, sound effects. And dollars, or what is this? This is average dollars. And what I expect to see is a distribution that's centered around 50. We'll just keep that as like that. And then we'll say average dollars. Oh, I hate doing abbreviations. It's terrible. I never know what I call things if I do that. Average dollars dot append this thing. And then down here, we'll do plt.hist. Average dollars. And then we'll put in a bunch of bins. Let's start off with 50 and just see what that looks like. It might look terrible. Here, I'll make that separate as a matter of fact so we can play with it. And put our bins here. Oh, I hate when it does that. There we go. We'll make it 20. There we go. So 50 is definitely in the middle. It's a little off center, which is kind of funky, but it's not really, it's random. What are you going to do? And we could do 10,000, just make sure it looks beautiful still. There we go. So that's a basic kind of Dirichlet introduction. It's really awesome. This gets used for other things, which I don't completely understand how it gets used for them. But I think it even gets used in, there's latent Dirichlet allocation. I think I might actually use some of this stuff, but I don't know exactly how. I want to learn someday. If you know how, come talk to me and drop knowledge on my head. It'd be great. Anyway, any questions on this? Yeah?
How are these two distributions different from oversampling on just the bootstrap?
Oh, that's a good question. So what's interesting is these distributions. So his question was, how are these two distributions different from oversampling on our discrete distribution from up above? Like, how do we know how many times to sample from this thing, basically, right? What's cool about this is since we're actually sampling from like a math model, right? So we have a Dirichlet distribution, we have a beta distribution. Let's go up to the beta. It's going to be a lot easier to kind of talk about it there. The beta distribution just has baked in the variance. So for example, here where we say, I'm going to just totally screw up my example so that way I can play with this. And again, this is why that data is there. You guys can play with this stuff. But let's take this out and let's just put numbers in here and just see what happens. So if we had a perfectly fair coin, and let's say we have no prior information at all. Let's start off with what that looks like. So right now we have no information, right? So we just have this perfectly flat landscape. So what's interesting to your point is I'm sampling this 15,000 times, but I have a super wide distribution, right? So this doesn't work the same way as discrete distributions do. This actually in the function is already taking into account that I'm only giving it 2 data points. So if we start to actually say, like, let's keep it a fair coin and just see what happens as we start to narrow this. Actually, this is fun to step through too for people who haven't done it before. So we do our next coin flip. We get this as an answer from the beta distribution. And we're not having to do any logic or anything. This just comes out of the beta distribution. I love this function. It's great. So you pull that out and you're like, okay, so now that we had, let's call this over here, let's call it heads for right now. And this is tails on this side. I'm going to make a little note for myself so I remember. So tails to heads. Okay. So now we say, okay, well, heads looks a lot more likely now because we flipped the heads to begin with. So if I were just a betting man and if this thing was weighted in any direction, it's probably weighted towards heads. But I'm definitely not going to rule out the fact that it's 50-50 chance still. In fact, a lot of things are still really possible. I've only seen one thing, so who knows what's going to happen. Then let's say we flipped the coin again and we get tails, right? We get this. And so what's cool about that is, again, like no matter how I change this number, the general shape, God, that's ugly. But the general shape stays roughly the same, and it's just we increase the precision. So this is really back to the precision number again, and these numbers over here are what are deciding the variance. And what gets weird about that, oh, go ahead while I'm still on that same subject.
So when you had 1 and 1, I mean you had 1 head and 1 tail, you got a flat distribution.
Yeah.
And when you had 2 and 2, or 2 heads and 2 tails, for example.
It's really technically the beta distribution. It starts off, you have to start with like, you can do 1/2 and 1/2, but I have no idea how to explain that to anybody. But you start off with 1, and it's technically like you have 0 plus 1 and 0 plus 1. So there's not technically any flips, and that's why it's a flat distribution. And then when you have 1 flip, that's why it's now 2, is because it's really just the number of heads and tails you've had, number of successes and failures, plus 1. And that's just a property of it. Like if I put 0 and 0 into this, I would get an error. It'd just be like, cannot do. So that's why. And that leads me up to the other point, which is, so with that property, the same thing happens in Dirichlet, where basically I end up having to make these distributions that have many, many ones. But what else is interesting about that too is that means that you end up with a lot of prior information that actually is meaningless. So like when you do like every single penny, I've done analyses before on every single penny from like $0 to $100, and you end up with then what, like 10,000 bins essentially. And so when you get any data point in the middle of that all of a sudden, you still have you actually get like a very narrow variance, and you actually have like, it looks like a much higher confidence than you actually really do until you start seeing more data come into your sample and stuff. So it's an interesting different world. One of the advantages of the Bayesian bootstrap over the normal bootstrap is the normal bootstrap, you just kind of have the data that you have. The Bayesian bootstrap is more probabilistic, so what you're sampling out of there, you can actually get to like expected values of these different parameters. It's actually saying like this bin, like 33%, and it's just a smoother way of looking at it. They both basically approximate to the same values, but also Bayesian bootstrap is a little cooler. That's really it. A little more precise. That's really kind of it. Other questions about that craziness? I'm not going to go too deep into it. We have another 25 minutes, so. All right, cool, we'll move on. So we talked a little bit about split test conversion already. We're going to hit it one more time here, and we're kind of going to use all the stuff we've been using up above. And oh, I did a better job naming this stuff. Like I actually might get through this without too many bugs. That'd be great. So we start off with split test, and we have different sample sizes of these two different groups. We run it through doing an analytic simulation here with a beta distribution and plopping in the orders and visits that we have as the successes and the total number of failures. So this is actually run. Minus orders, like that. I think that should be correct. And then we can just plot them basically. And this just shows us, okay, so just given nothing else, like this is what we think the true values of these groups would be in. And what's interesting, you can basically take this data and you can say, well, what happens if we multiply each of these things by 10? So it should be still hovered around the same, they should have the same average still, right? But we'll see a difference in their variation, the variance. And so now you can kind of get a feel for, oh, okay, well, if this was the case, then this gives me just some sort of an interval that I can communicate to people. So I can say like, oh, it's somewhere between, and again, we can get the exact number, but I'm going to eyeball it. This is somewhere between 16 and 20%. This other one's somewhere between 14 and 18%. They kind of overlap. If we want to have them completely not overlap anymore, throw more data at it, and we'll be able to do that. But in the meantime, this is what we got. So let's see if just the differences between them, even though they overlap, maybe the differences between them are still significant. So we can run a simulation to check that out. And that's what we do down here. Oh, and I actually do the exact interval, which is nice of me. And there you go. So still technically zeros within the interval. So we're like, well, don't know. So I actually like, there's a few different ways you can do this like we were talking about before, where you can take everything that's less than a certain value and just say like for 0, you can say 95% of the data lied less than 0. So I think that this is then a worse change, or take the opposite and say it's a better change. But I think what's really cool about doing the credibility interval is it's almost like Occam's razor. So instead of you having to account for every single hypothesis from 0 to negative infinity, you're accounting for just a small number of hypotheses between like -1 and 1 or something like that. And they have the majority of the weight behind them. So I feel like there's a lot more, I have no proof for this, but from in my head, I feel like there's a lot more credibility or validity to finding the center data and using that as your hypothesis region versus the stuff that's going on way on the edges. Because especially a lot of times too, you're like, you'll get answers when you do lift, where it's like, you could basically model this, here I can kind of show, in this way, where you could say, take this thing, divide it by the other thing, and then subtract 1 so you can find the percentage lift. That's a fun one, but then your bottom part can equal 0, and then you start getting some weird results. I don't know what'll happen, let's see. There we go. So now we have it based on lift. And sometimes what you'll end up getting out of this too is if you have a 0 in the thing that you're dividing by, then you'll end up getting like infinities in here, or at least like undefined things. You don't know what's supposed to happen. So it's a little bit harder. But anyway, so that's another option. So for those of you who are kind of curious about split tests, does this make sense? Any questions about this? How you would use this for analysis? All good? All right. Cool.
Practically speaking, you would run your test A, you measure how many visits in order, and run your test B with different set of inputs and measurements, and then you report back your findings. Is that the practical application here?
I think so, and I just want to make sure I'm understanding you correctly. They would run at the same time, but yes, like I would run both the tests, get back the data, and so that way too, like it's a perfectly even split, ideal random type of thing. But yeah, exactly. Then I could report back results. I could say like, so, and what's cool about this method too is again, like deal in terms of ranges and just be able to tell people this was somewhere between this range is what the true value is. This one's somewhere between this range. And everyone just says, but we want to know, we want those intervals to be smaller. And we're like, great, that's a great conversation to have. Yes?
So your choice of the beta distribution here, right? One criticism that sometimes we'll face, in the Bayesian land, I guess, is like, it kind of requires expert knowledge to choose intelligently the proper distribution.
Yeah.
So what would you say for?
I consider us all experts in this room. Like so, and that's fair. So there's a little bit of math if you go the analytic route, right? Like you do definitely end up having to start figuring that stuff out. Like I showed above, like we can just use bootstrapping to do this stuff, but it's a lot faster and simpler if you don't have to do that, and you can just use this instead. So I would say if you want to have zero knowledge, bootstrapping is amazing, and it'll get you pretty far. Like it's not for everything. There are flaws with it. People have valid concerns sometimes, but seriously, like 90%, 95% of what you do, you can get really far with bootstrapping. This is for, as you just trying to start learning, this kind of gives you a path into learning more and more about distributions, pulling that stuff in, and it gives you a path onto Bayesian statistics as well, which kind of, to me, brings in a lot of the benefits you get out of bootstrapping and out of simulation, and starts pulling it more and more into probability and statistics. So that's what I would say. I would say that you have a learning path ahead of you. Like if you were that person, like here's your trail. You start here, and then there's little cookie crumbs. You just keep following them. It's basically what my path has looked like. So, answer your question? Okay. Did you just ask that question so I'd say the answer you were thinking?
That's a question that people have asked us basically for a really long time, and also our biggest criticism, right, in science.
Yeah.
So the frequentists would say you have no right sort of assigning arbitrarily a distribution. In fact, your method is
Yeah.
Inferior because of that.
Yeah. That whole argument. I think there's a lot of value from both sides. Like I kind of pull from both. I like the idea of hypothesis testing. I like the rigor of it. Frequentist tests are fast, crazy fast, like t-tests go like that. There's no worries about sampling or any of that other crap, and they work great for a lot of things. I think it was like a couple years ago or a few years ago. I was basically thinking about it. I was just like, so I either have to commit to one or the other. Like, there's so much stuff you can learn in data science. You have to start choosing stuff and just say, look. I'm also lucky because I was already a programmer. So I'm like, I've already been a professional software engineer. I don't need to know what it feels like to push code out to production. I felt that before. I've broken things, big things before. It's great. But now in this world, I'm like, so I know the thing I want to focus on is either going to be Bayesian statistics, some other thing of machine learning, frequent statistics. What am I going to like really root in on? And Bayesian statistics was something I started looking into. I started hearing about it first like a couple years ago, 3 years ago. And the thing that, at first I was just like, this is hype, this is stupid, like it's just another way of doing things and people are being ridiculous. But then I kind of realized too, the reason why, for myself at least, this really resonated was because it's the idea that you now just have a general framework for how you approach statistics. And it's like plugging in Legos. It's not, did you use the Kruskal-Wallis test method and does it pass all these other different criteria? Or did you use the U-test because you're dealing with like a walled whatever test for non-parametric data? Like you ask someone about, oh, do you know how to handle non-parametric data? And they'd be like, whoa, well, I didn't take that statistics class. Like I just deal with parametric data, everything's normal. And I like this because everything applies pretty well across the board. You just have to learn these other things, but they're all within the same framework. It just seems more consistent to me. So anyway, my rant. Other questions before I stop ranting? All right, cool. Scrolling on down. Oh, this one's fun. You've all probably already done this because we're all data people. Monty Hall's problem, right? Like, is there anyone who hasn't done this problem before or explored it, and is there anyone in this room who doesn't accept that it's better to switch the door? Raise your hand. We won't laugh too hard. I don't blame you for not raising your hand. So this was something that I think is a great opportunity for us. So like being able to say like, you know what, I don't actually, like I get that the answer is this, but that's kind of dumb. So I want to simulate it because that seems really, really ridiculous to me. I've seen problems like this on Twitter with like people who are big analysts, and a lot of it's about the way they word the problem. But being able to simulate, I can say like, this is what you said, right? And they'll be like, yeah. And I'll be like, I run it, and when I get down to the bottom, when I switched, I won twice as many times as when I didn't switch. So you agree with me then? So we're saying, because that's what's important. So this is basically just me kind of showing, and this is very Monte Carlo. Like you see, I have doors in my code. I have someone making a random choice. I have a switch choice occurring here, basically, and then I just run over a whole bunch of times and just aggregate my number of wins. And I have 1,000. I mean, I kept it even numbers, multiples of 10, so it's really easy to see what the percentage is because this has to have a percentage in there somewhere. So, and they have to add up to 100%. So it's pretty easy to see what it is. But it's a little bit kind of a long simulation for such a simple problem. Kind of like it's kind of annoying to have to write 30 lines of code. Which is another issue with Monte Carlo simulations is that sometimes you can just do the math thing and have a beta distribution, or you can write 50 lines of code. But the 50 lines of code work, and if you understand them, and it's really easy to look at them, then that's great. Any questions about just this simulation? Cool, okay. Then we will move on. So this next one is about sample size. And this is one where people are like, oh, that's really complicated. This is what really got me looking into simulation when I first started off, was just because I just honestly was ignorant. I didn't know any better. So I was just like, well, I know I could just run this a whole bunch of times and see what happens. And so I did that, and it sort of helped me understand more like how many samples I needed when I wanted to run certain split tests and stuff. So here basically I have, again, I'm generating data to replace data that I don't have. But in this case, I'm trying to analyze how the test performs on different sizes of data. So in real world, I would actually do all this with generative data because I'm not actually trying to give an analysis of how a feature turned out or anything. I'm trying to understand how does this test behave at different parameter values, basically. So I run over this. Excuse me. And let's see, the first thing that I show here is basically, try to remember what this code is. So I'm getting basically a number of times that, I'm basically just doing a histogram of all the different p-values I get out of this process. So I say that I have one normal distribution that's 20% higher than the other in terms of the mean. And then I sample 80 things out of each one of those, 80 samples out. And they have a variance of 1, both of them do. And then I just run through that a bunch of times with the t-test from stats models, which I think there's a better one in SciPy. Stats models it has some cool things. I think linear regression is nice in stats models, and I think other stuff is kind of rough. But anyway, so I get the p-value out, and then I just make a histogram of those, and I do this. And I'd be willing to bet that if you haven't done too much of simulations, you've probably never, ever just done a histogram of p-values or seen what that actually looks like. Like, to me, this is awesome. Like, no one's ever actually just shown me what happens on these tests. They're just like, well, if it's p equals less than 0.05, then boom. But with this, you can actually see like, oh, I have something here which is actually supposed to be a win, but because the sample size is so small, I get answers kind of all over the board. So it's great to know that that happens, I guess, to me. And then if we want to change that sample size, we can have fun and do it correctly. Make sure we get the same results. This is just a good way of change management in live coding land. Let's run that. What? Oh, stats models. My bad. All right, so we have roughly the same kind of look to it. Now let's see what happens if we multiply this by 10. And call your shots ahead of time so you know you're in control, right? You think, if I multiply the sample size by 10 of both of these different groups, I should have very few p-values above 0.05 because it's a pretty big change, 20% increase, right? So we run it, see if this matches our gut. There it goes, Vroom. All the data is over here somewhere around 0.05 or less. So again, fun way of exploring things. But we can go even further with it too. So we can actually look at power essentially, like how likely are we to see an effect given that there is one at different sample sizes. So this next simulation does that. And let's run it and see if I can screw everything up. Wait for it. The tension. It's really dramatic. The fun of simulation. Waiting. Oh, there it goes. Great. So this plots it out for me. And I think I was using, okay, so I said if the effect is 15% on a normal distribution, this is the way that sample size turns out. And so rather than having someone have to graph this for you with some sort of crazy calculations that they do, I don't know what you do. I've never learned how to do this in math. I do simulation. But you can see also too, it's kind of spiky. Those spikes aren't really real. It's just because they're simulating and things are rough in simulation land. But you get a really good feel for this. If you're talking to a business person, and also too, like when you try to stop a test, you never stop it on exactly like, in this case, what are we at? 95% would be somewhere around 1200-ish, 1300-ish. You're never gonna stop it at exactly 1300. It's not gonna be like, you're always gonna be like over or under by some amount. So it's not really a big deal. I think the really big deal is you don't ever wanna be like, well, I think it'll only take us 400, and then actually you need to do 1,300 or 1,400 samples. So this is a great way of just generating a guide. And when people want to see, like, well, why are you saying that? I basically show them my code and be like, well, I'd show them actually an IPython notebook. I'd walk through it and be like, here's the different graphs of what happens at the different sample sizes. So it becomes more and more likely that we'll see the change. And this is the point where we become pretty darn certain. And we can have discussions around here in the upper part of this curve. You want to go too far below, like 80% is like the lowest. I think we did like I've done like 1 or 2 tests before that were that low. But yeah, anyway. Yeah.
I might have missed what you said because I was behind it, but
That's fair.
In practice, you would really, I guess, start with some effect size. Like in this case, it was like a 0.2 difference in some effect size you wanted to be able to detect. And
Yeah.
say something like, I want to be able to
Yeah.
X% of the time, and then you just update your sample size to be like.
Yeah, exactly. And that's a conversation too, because then you change this to, and let's see how hard this is going to be. Oh, I think it'll be easy. Let's say we change this to 0.05. And then I can show someone like, well, this is what happens when you have these different sample sizes at that effect size. It'd be great to be able to plot this in 3D, but that would take forever. Yeah, it's just running a t-test. So I have control data, like a whole list of control data. I have a whole list of variant data. And then it just outputs the t-statistic, the p-value, and the degrees of freedom. And I just want the p-value. Yeah. And then here's the one for only a 5% effect. And you can see like even at 1,600 samples, we still never get to above 30%, which is very different from the previous effect size that we had. And so this is how you can just play with this stuff and move through it. And we have a little more time, so let me just get through, speed up a little bit. So this next one is really cool. So this was actually something I learned by doing simulation, which is, so if you have a binomial test, right? So you want to test heads or tails, just Boolean data, right? How the sample sizes or how the power is affected by the base rate that you're actually testing against was really surprising to me. So in this, we kind of get into that. So what I'm doing here is I'm basically saying, so this is different, what is this one? This is actually going to be different percentage of times that we get a p-value that is less than 0.05. And this is based on the actual base rate conversion, or the actual base rate of conversion. And so this is a percentage change. So a percentage change of 4%, which then means that the larger that our base rate gets, of course, the larger the change that we're actually identifying in the data, right? So that makes sense that it gets easier the closer we get to 100%, because it's all of a sudden like, instead of trying to change like a half a point change, you're trying to test for a like 2-point change. So that's changing the whole time. So that's one curve that's interesting. But then if you say like, well then, what about if I just keep a constant point change? So I want to see like literally like a, what did I end up looking for here? A 2-point change in the population, right? A 2-point change in the rate. So like if conversion was 2%, now it'll be 4%. If it was 32%, it'd be 34%, et cetera, et cetera. What does that look like? And what's interesting is you get this dip, this valley. And does anyone know why you get that dip? This didn't make sense to me until I thought about it for a little bit. Any guesses? No, I understand. All right. So what's going on is if you have, like let's say you have a coin and it's always flipping heads. And then you're like, but I changed something and now I want to see if it flips tails more. If you get a tail, that's pretty awesome, right? So on the left and right sides, there's very little variance in what's going on. You have almost always heads and almost always tails. In the middle, things are just going wild because it's just a 50-50 chance of anything happening, and things get a lot harder to detect. And so, like if you have 50-50 heads and tails, that means like so you get an extra like 10 heads. Does that really mean anything? That's actually really hard. But if I only have a 2% chance of getting heads and I get 10 extra heads, that's a really big deal. And so that was actually a really interesting thing to see in simulation land, and that's something I shared with like people as well. It's just like, well, it's actually kind of frustrating that if you have like a really solid conversion rate in the middle of like the spectrum, it actually might make your testing a little bit harder. So there's that. And then we have more stuff to go through, but you have it all in the notebook. So I'm going to leave it. Actually, on the next section here, I get more into actual just raw Bayesian statistics and going through like a probability problem of you roll 5 dice that are all different sided kind of dice. What's the probability that if you rolled a 7 that you have a 6-sided dice or an 8-sided dice, et cetera, et cetera. You can go through that and see how I do all that. We have like 5 more minutes for questions, so I thought I should probably end it there. So, any questions? Anything else that's lingering in the back of your minds? Yeah?
I see that you have just a product funnel example further down. Can you just talk through that real quick?
Yeah. So he's asking about the funnel example that I have in here that's near the bottom. And essentially the idea was just to say, like, so if you just have basically X% of conversion rate, like you know conversion rate for the different channels you have going into your website, you know roughly how many visits you expect to see. Can you just take all these different parameters and just kind of aggregate them into a model and just see what the variance would be on a day-to-day basis? That's mainly the whole point of this. The question is just kind of how, given all these different factors, what kind of variation should you expect to see on a day-to-day basis? So that way you know like when something's on fire or something's going really, really well. So then in here, basically all I'm doing is just writing down the inputs to the data, kind of following that 5-step process from the very top, just organizing my information in code. And then I'm going through and just using, like, for example, I use a normal distribution just so that way I can perturb the numbers that I have. And I perturb them by, I think I give them a a variance of 10% for each one of these things. And so I'm just kind of adding noise into the model and saying, like, so if I just start sampling randomly from this normal distribution that's like my SEO visits, and this other one's about SEM visits, other visits, return visits, and then I have the conversion rates as well, then I can just start coming up with an actual number of orders I should see on a day-to-day basis. And then what I also did down here is I gut checked that. I said, well, I would expect this, if I did this really simply, I would just multiply the conversion rate by the number of visits I expect every day and just add them all together to get all of the orders. And that number is 56,500, and that's roughly in the middle of this, which is another, for the person who was here, that idea of like, how do you check this stuff? Like, that's how I checked this model really quick. It's just said, oh, that's in the middle, and the variation somewhat left to faith. But I also checked that as well by trying to increase some of the variance in my different normal distributions and stuff to allow more noise in, and yeah, cool. Yeah?
I'm fairly new to this type of modeling, so I was wondering, is there any reference material or books or what that you really suggest?
Oh God, there's so many books. So simulation specifically, or are you thinking Bayesian statistics, or?
Just simulation and Bayesian statistics.
Bayesian statistics, start with Think Bayes. That is an excellent book for beginning. And for the simulation stuff, there is a really good book called Simulation. Let me look on Amazon really quick so I can get you a name of it. It's the only book I found on simulation that I really, 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 really liked. And I probably won't be able to see. I'll only know it visually. But if you gave me a card or something, I could tell you the book when I find it when I get back to work. Cool. Other questions? All right. Well, then, thank you, everybody.